Okay, so yesterday we talked about how to graph equations of lines, and I'm just going to revisit that. So let's revisit from yesterday. Revisit graphing y equals mx plus b. Recall that m was the slope or steepness, and that b was our y-intercept. So let's just revisit. So as an example, let's graph y equals, how about we do 3x minus 8. So I don't have a fancy graph here, but I'm just going to draw a graph. So I've got my axes, and let's think about how we go about this. So remember, the first step was to plot our y-intercept. So in this case, our y-intercept is this guy right here. So it's -8. So we're going to come down here, and you can envision 1, 2, 3, 4, 5, 6, 7, 8. So in around that vicinity, we'll mark it. There's -8 as my y-intercept. And then we had to, as our second step, we need to find our slope fraction. So in this case, our m is equal to this value right here, right? Because m is the first value and b is the last value in this position, but it's always when it has to be against the x. That's the important part. Anyways, m in this case is 3. Well, I want m as a fraction, and clearly if we look at this right now, m isn't a fraction. M is just an integer, or a natural number in this case. And so we can always turn any integer into a fraction by putting it over 1. So I come over here and I want to graph this. So remember, slope as a slope fraction is rise over run. And remember, just as a rhyme, rise comes from the y's. And this is obviously, or not obviously, but we remember that the y-axis is the one that points its own direction. It says it goes that way. And then the x-axis goes across. So if this has a slope of 3, it's 3 over 1. And I know that it's a positive slope. So in the grand scheme, this thing's got to look kind of like that. So if I wanted to plot this as slope of 3 over 1, we're going to go up 1, 2, 3, and then over 1. And we're going to plot a point. We're going to repeat that. We're going to go up 1, 2, 3, and then over 1. And we're going to plot a point. And then we would go up 1, 2, 3, and we go over 1, and we would plot a point. And you can repeat that as many times as you want. But the long and short of it is what we have now is our line. Okay, so that isn't new. That's what we played with yesterday. And so all good. We should hopefully remember that pretty well. But what I want to point out is has to do with a table or an equation, a y equals mx plus b. It's sort of like, not sort of, it's a machine that it takes x values and it spits out y values. So when we were talking about 4 forms of a relation, we talked about 4 forms of a relation in the last little while. Remember 4 forms, so 4, oops, wait, I've got a line here, excuse me. So 4 forms. Remember that the 4 forms were, first off, we had words. And then second, we had equation. I mean, the order didn't really matter. We had 4 of them. And then third, we had a table of values. And then fourth, what we had was we had a graph. And so we just did an equation, we did graph. What we haven't done is a table of values. And so I want to just show sort of how a table of values works with one of these equations. And so we're going to examine that. So here's how it would work. Envision the following. I should have made that longer. I'll make this a little bit bigger like this. There we go. So table of values is going to look like x, and we're going to have some x values. So in this case, you know, typically speaking, I go like -3, -2, -1, 0, 1, 2, 3. And then over here, instead of just being y, it's going to be y equals, and the equation we used. So the equation was 3x minus 8. So 3x minus 8. Now I probably haven't given myself quite enough room here, so let me just clean this up a little bit. We'll put those in a minute. So back to here. So the way we use a table of values and how we can generate a table of values is as follows. This equation is a machine, and this machine takes in x values, and then it spits out y values. So I want to show you how that works. So we're going to take y equals 3, and then we're going to substitute this -3 in for my x, and then I'm going to simplify. So I'm going to just put this into my calculator if I need to. 3 times -3 is -9. -9 minus 8 is -17. So over in this last column, I'm going to do x comma y. And what these are going to be are these are ordered pairs. Okay, and so this ordered pair has this x coordinate, -3, and this y coordinate, -17. So -3, -17. Okay, and we do it again. I'll do it for -2 now. And so we have y equals 3, and I'm going to substitute that value in of -2 minus 8. So all I've done is I've replaced this x with this value right here. So we're going to have 3 times -2 is -6 minus 8, which is going to be -14. So another ordered pair then is -2, -14, -2, -14. And then we could do it for -1 as well. Let's just shift these guys down, get rid of those, there we go. -1 is going to be y equals 3 times -1 minus 8. So that's going to be -3 minus 8 is -11. So this ordered pair is going to be -1, -11. And then we would do it for 0. Now 0 is an interesting one, and we're gonna come back and we're gonna talk about this. But 0 is of particular interest for an x value of 0. So we're going to do y equals 3 times 0 minus 8. Well, 0 times anything is just 0. So then it's 0 minus 8 is just -8. Now look, this is what's pretty crucial here. -8 and -8. Now there was no coincidence there, right? Because if I take the 0 and I put it in for my x, what's going to happen is it's going to cause this whole term to go away, because 0 times anything is 0. So when the x value is 0, we're always just going to be left with my b value, remembering that this is really y equals mx plus b. And the b value is all that's going to be left, because when my x is 0, this whole term is going to have to go away. And so, all right, we can continue on with our graph here. And so we would have 0, -8, and we could keep going. I'm only going to do a couple more. So y equals 3 times 1 minus 8. Well, that's going to be -5. And so it would be 1, -5, and 2, y equals 3 times 2 minus 8. So 3 times 2 is 6, minus 8 is -2. So that's -2. So then we're going to have an ordered pair 2, -2. Now, if we actually were to look and plot all of those points, some of those points would be, well, that'd be one of them, that'd be one of them, that'd be one of them, and that'd be one of them. So this table of values, if we didn't know how to graph by plotting our y-intercept and using our slope fraction as rise over run, another way, sometimes the first way that teachers will teach students how to graph a line is by creating a table of values for plotting all of these ordered pairs. Now that's pretty slow going, but it would 100% be a valid way to do this. So that is a viable option for graphing. What was key to all of this, I guess, is I want to demonstrate that an equation, y equals mx plus b, is just a machine that can tell us where an ordered pair is according to its x value. So I'll try and clarify that with another example. So imagine I said an equation, which is going to be y equals, let's say, negative 3x plus 8. Is that almost the same as what I had up there? Almost identical. Let's change that around. That's too similar. Let's get rid of that. So how about y equals negative 5x plus 3. Okay, that's a little bit different. Where does the line pass through when the x value is 1? So we could approach this in two different ways. One of them certainly much more efficient than the other. I'm going to show you method 1, which is the less efficient method to begin with. So method 1 could use the, that's not what I wanted. Method 1, we could do it graphically. And again, if I had some graph paper on here, it would be, more accurate, but I'm going to go ahead and I'm going to graph this one. So remember that we start with the y-intercept. So the y-intercept is 1, 2, 3. So it's about here for 3. And then the slope, so my m value is negative 5, but I want to turn it into a fraction, so over 1. So because it's negative and it's a big number, I know it's going to end up being really steep. So negative 5 would be 1, 2, 3, 4, 5, and then over 1. There's a dot. And then 1, 2, 3, 4, 5, and over 1, and there's a dot. Right? So this is going to look something like that. And so if I wanted to know, the question specifically says, where does the line pass through when the x value is 1? So here, again, I wish I kind of had a scale here, but I don't. There's my x value of 1. If you were graphing along on graph paper, you would find out that that value is negative 2. And so, the answer to that question would be when x is 1, the y value is equal to negative 2. Right? So there's my answer. So that's the first method, which is valid. It's 100% valid, but graphing can be slow and it's not always very accurate. And it's okay because the x value was 1 was pretty easy. But imagine I said the x value was 150. You'd have to be doing, down, over, down, over, down. And it would take, you'd have to have an enormous sheet of graph paper and it'd take a long time. So there's a better way. So that was method 1. Method 2 is the better way. And that is, of course, to observe that an equation, y equals mx plus b, is simply a machine that takes x values as inputs. So I want to know when x equals 1, what is going to happen to my equation. So the equation I'm using is y equals negative 5x plus 3. So it's going to be negative 5 times 1 plus 3. So I'm just going to substitute this x value of 1 into the equation. And I do that, and I'm going to get negative 5 times 1 is negative 5 plus 3 is negative 2, which comes as no surprise because we already found that graphically. But certainly, this is much more viable, right? And so I kind of mentioned the idea, what happens if x was 150? So, I mean, when we're dealing with an equation, it's not really any more complicated. So imagine if x was equal to 150, we could do the same thing again. We could say, oh, well, y is going to be equal to negative 5 times, in this case, 150 plus 3. So I'd break out my calculator. Negative 5 times 150 is negative 750 plus 3 is negative 747. So it didn't really matter there. In either case, we were able to do that pretty handily. So an equation is simply a machine that takes, generally speaking, x values, and we can use it to follow its own instructions, and it will generate y values for us. Okay, so that's good, and I'm happy about that. It's nice. It can, and it provides another way that we can find some information. But I want to use the idea about an equation generating values, and I want to explore the idea of intercepts. Hence the name of the note was intercepts. If we scan back up here, I think it was. That's what I called it. That's what I called it. Intercepts. So I'm going to come back down here, and I'm going to use that to find intercepts. So finding intercepts. And we're going to look at finding both x and y intercepts. Now you might think to yourself, well, finding the y-intercept is not going to be any challenge whatsoever. It's just always going to be the b value. And you're sort of right, as long as we have the equation in y equals mx plus b form. But I kind of want to show, again, why that always works. So if we think about an equation, y equals negative 8x plus 1, as an example, and I asked, what is the x-intercept? Okay, so what is the x-intercept? Well, I mean, we know simply because of y equals mx plus b that the y-intercept in this case is 1. But I want to explore why, that's important to know that the b value is the y-intercept. But I kind of want to explore why it makes sense that the y-intercept is this number hanging off the back here from a graphical and a table of values perspective. So here's a graph, and I'm going to graph this really quickly. So it's got a y-intercept up here of 1, and it's got a slope of negative 8. So it's super steep on a negative slope like that. Okay, so it looks something like this. And, if I had the graph, by all means, it'd be really, really obvious that the y-intercept is, of course, right here at 1. That's where the y-intercept is, right there. But if we think about y-intercepts in general, so in general, y-intercepts all are of one particular form. And this is going to pull together a few of the different things that we've done. It's going to look at some Cartesian plane coordinates, and it's going to give us some understanding. So we know that this is the y-axis, right? The y-axis is going up and down. And if we think about all the different points that exist on the y-axis. Imagine I asked every single student in the class to place a point on the y-axis and determine the ordered pairs. Certainly some of you will end up with the same ordered pair, but certainly not everyone would. So, maybe someone has their point here, someone has their point here. Someone might put it right on the origin because that's also on the y-axis. Someone might put their point here. And if I ask you to all write your ordered pairs on the board. Now these are all y-intercepts, right? Because they're all on the y-axis. So if I asked you to write your ordered pairs, here's what they would look like. Maybe this one was 0, 9, because it's way up there. 0, because the x-coordinate, we didn't move left or right at all. It's right on the y-axis. This one right here is 0, 1. The origin is 0, 0. Maybe this guy down here, it's 0, negative 4. This guy here would be 0, negative 7. Notice what they all have in common. Every single one of these things has an x value of 0. That's not coincidental. So in general, y-intercepts are of one particular form. They're ordered pairs always have an x-coordinate of 0. So they're always going to look like 0, comma, some number. Right? So it's always going to be 0, comma, some number. So, these are all examples of y-intercepts. They're always going to have 0, comma, a number. And that's really important to us. So if we, hopefully that makes sense to you, because if the x-coordinate was anything other than 0, so imagine you're like, oh, my y-intercept has a coordinates of 1, 5. Well, that would be over 1 and up 5. It wouldn't actually be on the y-axis, so it would not be an ordered pair. So that one just flat out does not qualify. It does not meet the criterion of being a y-intercept. So how is that useful to us? Well, look at how this is useful to us. What we can do now is, if we wanted to examine what is the x-intercept, or sorry, goodness gracious, I just noticed this now. This should be what is the y-intercept. We'll come back to x-intercepts in a bit. What is the y-intercept? Well, I know that the y-intercept has an x value of 0, right? Every point on this axis has an x equals 0. In fact, if you think about what we did with graphing lines yesterday, the y-axis's equation is x equals 0. Remember that when we had lines that looked like y equals 3, that was a horizontal line at 3. And y equals negative 2, that was a horizontal line at negative 2. If we had x equals 5, what that was it was going to be a vertical line at 5. So the vertical line that is the y-axis is actually x equals 0. So why that's important to us is, if this equation is a machine that takes x values and gives y values, like we just used it to be up here, right? That's what we did with this table of values up here, was treat it like a machine, give it an x value, and it gave us a y value. If we go back down here, I can find, so to find our y-intercept, we know that that must mean that x equals 0. So, yes, we do know that the y-intercept is plus 1, but I want to show you why, from a mathematical standpoint, that actually works. We know the x value is 0. So if I use this machine and I put in an x value of 0, what we can do is we can simplify. Negative 8 times 0 is 0 plus 1, and it's of course just 1, which we already knew because of this, but this just reinforces that all y-intercepts have an x value of 0, and as soon as you have an x value of 0, that means that the mx part of your equation is going to fall out and you're just left with b. So if we think in general, right, we have y equals mx plus b. If I want a y-intercept, I know that means x equals 0. So in general, what I can do is I can say, oh, that means that y equals m times 0 plus b. Anything times 0 is 0, so that's 0 plus b. which is just b. Okay, so our y-intercept is always going to be b, which is what I instructed you, but this is a mathematical demonstration of why that actually works. So that is how I'm going to get y-intercepts. I'm going to take the x value and I'm going to put in the x value of 0 and find my y value. So I'm going to just save this and then open up a new one. So I'm going to put this on my desktop. So this is intercepts. Save that guy. Actually, I'm going to save it as a JPEG so I can share it with the class. Intercepts, there we go. Good. Okay. And then I'm going to open up a new file that we can keep working on. I want the notebook template. Okay, there we go. Awesome. So I want to continue on with the intercepts. So if we think I said that it will always work to find intercepts. Now, equations don't have to look like y equals mx plus b. Equations can look like something else. So 3x plus 2y equals, we'll make it an easy one, 12, let's say. This is an equation as well, right? And we'll graph these in Desmos. And in fact, you could do that today if you wanted. You could check that out in Desmos. But I might ask, so this is not y equals mx plus b form or slope y-intercept form. This is a different form. And we're going to play with this a fair amount more. But imagine I said, what is the x-intercept of that equation? And I don't want x again, I apologize. I'm getting ahead of myself. I want y. Okay, what is the y-intercept? Well, we can use that same concept, right? So I'm thinking, a y-intercept has to be along this axis right here. And that means that my x value must equal 0. So I can come back over here and I can say, well, you know what? I'm going to take and I'm going to change that x out because x has to be 0 for a 0. And so then I can say, all right, so that's going to be 3 times 0 plus 2y equals 12. Well, 3 times 0, that's 0. 2y equals 12. So that's going to be 2y equals 12. So if I want to know what the y-intercept is, all I need to do now is solve for y. So I'm going to divide by 2 and divide by 2. And I'm going to get y equals 6. So this actually has a y-intercept of 6. Right? So if I'm going to graph this thing, I don't know much else about it, but right now what I do know is it has a y-intercept up here at 6. So I know that. If I could find a way to get the x-intercept, well, we'd be golden, because then I'd have a second point and I'd be able to draw the line. But what's crucial is that anytime I want a y-intercept, I know, so therefore x must equal 0. Okay, so if I want a y-intercept, x has to be 0. Well, we're going to extend that. I said if we knew where the x-intercept was, wouldn't that be wonderful? Well, it would be wonderful. And so I want to use almost the exact same logic for finding, in this case I really do mean this, I want to find x-intercepts. Okay, so finding x-intercepts. If I want to find an x-intercept, let's do this graphically. Let's think about this like we did with the y-intercepts. X-intercepts would be whatever is along the x-axis. So I'm talking about all this space along here. I want to know where a line crosses that. Well, if we asked that same exercise, if I asked every student in the class to plot an x-intercept or a point on the x-axis and then find the ordered pairs, what would they all have in common? So, if I just drop on a few or maybe 4 ordered pairs, maybe this one would be -7, 0. This one would be -3, 0. This one would be, I don't know, maybe 2, 0. And this guy here, well, it would probably be 9, 0. What do they all have in common? Well, all x-intercepts have a y value of 0, right? There's my y value of 0, there's my y value, there's my y value, there's my y value. And think, if you're like, oh, no, my y-intercept, or my x-intercept, excuse me, is, 4, -2. Well, if I came along here and I went over 4, as soon as I look at this x-coordinate, if it's anything other than 0, I'm moving off the x-axis. So this guy would be down here, and clearly that is not an x-intercept, right? So that one wouldn't qualify. So what's key is that all x-intercepts have y values of 0. So that is vital. So what we can do now is, let's take this same equation, right? So my equation was 3x plus 2y equals 12. So given 3x plus 2y equals 12, determine, in this case, the x-intercept. Okay, we can do that. So if I think, x-intercepts, they're along here. I know if I want an x-intercept, that means that y must equal 0. So what I'm going to say is, if I want an x-intercept, it means that y equals 0. I'm going to take my equation, 3x plus 2y equals 12, and I'm going to take this 0, because it's for y, and put it in for y. So we're going to have 3x plus 2 times 0 equals 12. And then we're going to solve for x. Those guys are going to go away. So we're going to have 3x equals 12. I don't want 3x, I just want x. So I'm going to divide by 3, and we're going to get that x equals 4. So look what we've got. From earlier on, we found that the y-intercept of that was 6. Okay, so we have, this is our x-intercept, and we know that y equals 6 is the, of course, y-intercept, and that makes this really powerful, because look what we can do now. What we could do is we could actually accurately graph this line. So even though this is in different form, we can still do it. We found that it has an x-intercept of 4. So we're going to go out here and, there's an x-intercept of 4. And it has a y-intercept up here of 6. There it is at 6. And so we actually have an accurate line. What we can do is we can graph it through like that. And there is a super accurate line. So we have got a second way now. I didn't even have to figure out what the slope was and use a slope triangle or a slope fraction. What I could do is I could actually create our graph of a line using intercepts. So I'd like to do another example. I'm going to, put up another example, and I'm going to stop talking for, a minute. And I'd like what you to do is, I would like you to see if you can follow that process through. Actually, maybe we'll do one more together, and then I'll do that. So imagine that we had given, how about -4x plus 3y equals, 36, let's say. I would like to do three things. Find the x-intercept, find the y-intercept, and then I want to graph this. Okay, so three things we're going to do. We're going to take this equation, y equals -4x plus 3y equals 36. We're going to find the x and the y-intercept, and then we're going to graph. And I'm going to go through this nice and slow. So, first things first. We want our x-intercept. And I find it's often a good idea to just draw just a little teeny sketch to help me remember what's going on. X-intercepts happen along here, which means that y equals 0. So if I want an x-intercept, I actually write, oh, that means that y must equal 0. So I take my equation, negative 4x plus 3y equals 36. And I know my y value has to be 0. So it goes in there. So we have negative 4x plus 3 times that 0 equals 36. So then we have negative 4x plus, well, 3 times 0, that just goes away. So negative 4x actually equals 36. I'm going to divide by negative 4. I'm going to divide by negative 4. Those guys are going to go away. They're going to divide out to be 1. And we're going to get x equals, you can use your calculator if you need to, 36 divided by negative 4 is negative 9. So my x-intercept is negative 9. Lovely. Now we want to find our y-intercept. So if I want my y-intercept, I'm thinking, all right, back to here, the y-intercept exists there, which means that x must be equal 0. So I'm going to go over here and actually write it. If I want a y-intercept, it means my x value must be 0. Okay, so we're going to have negative 4, and I'm going to take that x value and put it in there. So times 0 plus 3y equals 36. 4 times 0 is 0, so it's gone, and I'm just left with 3y equals 36. Divide by 3, divide by 3, y equals 12. So look what we've got. We've got our x-intercept, and we have our y-intercept. So now all I need to do is I just need to graph them. Right? So if I want to graph these, let's actually Control Z on that guy. Make it bigger, make it up here. So there we go. Now, to graph them, all I'm going to do is I'm going to say, all right, I got a y value of 12. Again, I don't have a scale, but 12 would be up nice and high. So there's my y value of 12. I've got an x value of negative 9. So that's out over here. There's my negative 9. And so then my line would look like that. And what I've got is I've got, aside from the fact I don't really use a scale here, I've got a really accurate sketch of that equation right there. Okay? So think about the process we followed. If I have an equation and want to find the x-intercept, I know the y value must be 0. If I want the y-intercept, I want the x value to be 0. You solve for them. We've got our x and our y-intercept. We can put them in, plot them, and then we can make a graph. Let's try one more. This time I'm going to give you some time to try it on your own. Okay, so let's try this color here, whatever color that is. So imagine that we had the equation 5x minus 2y equals 20. Same three things I'd like you to do. I'd like your x-intercept, I'd like your y-intercept, and I would like you to then graph that relationship. Okay? So I'm going to give you a minute and a half. So go to town and then I'll take it up. Okay, there's a minute and a half, so I'm going to start working through this. First thing I want is an x-intercept. And I just remember it because if I want an x-intercept, it means that the y must equal 0. Or again, I think about my graph here and think, all right, x-intercepts are along there, which means that that y must equal 0. So I'm going to take my equation. If I want my x-intercept, so 5x minus 2y equals 20. And I know that my y value needs to be 0. So 5x minus 2 times 0 equals 20. 2 times 0 is just 0, so that goes away, and I'm left with 5x equals 20. I'm going to divide by 5, and I'm going to divide by 5, and we're going to get x equals 4. Okay? So there's my x-intercept, x equals 4. Lovely. And then I want to get my y-intercept. Okay, my y-intercept, I know that means my x value must equal 0. So it's going to be 5 times 0 minus 2y equals 20. Here's where you need to be careful. 5 times 0 is 0, so it's gone. Don't just think, oh, that means it's going to be 2y equals 20. This negative belongs to the 2y, and it's still negative. Okay? So I have negative 2y equals 20, but I don't want that. I want just y, so I'm going to divide by negative 2. Divide by negative 2, and we're going to get y equals negative 10. And there it is. So what I've got now is I've got my x-intercept, I've got my y-intercept, and now I want to graph it. So here we go. I'm going to graph it. There we go. So I'm going to graph that guy. So I got an x value of 4, so it's just out here at like 4. There it is. And a y-intercept of negative 10, so that's going to be like way down here at negative 10. And then to graph it, I'm just going to join those two. And I didn't do a great job. Let's pretend that's not going to work. I can't shift those ones. Let's try that again. There we go, like that. And what we've got is we've got an accurate graph. Okay, so I can get intercepts, either x or y, straight from my equation by knowing that I can put the y value in as 0 for my x-intercept or the x value in as 0 for my y-intercept. Now, I want to show you that, you know, this is a different form of an equation than what we've been using, but this same concept still works for y equals mx plus b. So I'm going to do one of those, and then we'll call this video quits. So imagine that we had y equals, I don't know, 3x plus 12. And I said, I want to know what is the, we'll start the easy one. How about the y-intercept first? Then I want the x-intercept. And then I want to graph this guy. Now, the reality is, if you want a y-intercept, you know what it is. It's 12 because it's the b value. However, we're going to follow that exact same process. I know that if I want a y-intercept, it's got to be along this axis, which means that x must equal 0. So I come along here and say, oh, y-intercept, I know my x value is 0. So I'm going to follow that same process. So y equals 3 times 0 plus 12. 3 times 0 is 0, that goes away. So I'm just left with 12. So there it is, y equals 12. We knew that, but it's nice to see a demonstration that it still works. How about our x-intercept? We haven't done an x-intercept in this form before. I know for x-intercepts that the y value must equal 0. Okay, that's okay, we can do that. So we had y equals 3x plus 12. But this is saying, oh, my y value has got to be 0. All right, so I'm going to put 0 in for y equals 3x plus 12. Now I want to know what x is, so I have to solve for x. But you know what? We're not bad at that. We know that we have to get the x all by itself. So what I'm going to do is I'm going to take this 12 and I'm going to kick it over here. Right now the 12 is positive, so when it goes across, it's going to become negative. So in theory, you could say 0 minus 12 equals 3x, because the 3x didn't go anywhere. 0 minus 12 is just negative 12 equals 3x, and then I'm going to divide by 3, and then we're going to have that Yeah, these 3's cancel out, and we have x equals negative 12 divided by 3 is negative 4. So there's what we've got. Look, we have a y-intercept of 12 and an x-intercept of negative 4. So if we look at the graph for this thing, let's think about if we graphed it the two different ways. So let's do it with the intercepts. Got a y-intercept way up here at 12. We've got an x-intercept at negative 4. So that's not out as far. Here it is, like right there. And we're going to get that that is negative 4. And we're going to graph it. Right? So here we go. Oh, that didn't work. Let's try that again. Close enough. There it is. There's the graph. Now, had we done it the old school way of graphing, right? Not old school, we just learned it yesterday, but the other way, we would have gone up here and we said, oh, it's got a y-intercept of 12. Absolutely. And then we would have said, what's the slope? Well, I know that the slope is 3, but I want a slope fraction, so 3 over 1. So that would tell me you need to go up 1, 2, 3, and then over 1. Boom. If I went the other direction, 1, 2, 3, and over 1, it'd take me to there. 1, 2, 3, and over 1, there, right? And so it ends up being the exact same line. Which one's faster? Well, probably that way of plotting the y-intercept and then using the slope fraction. But the reality is, it's good to know that we can also do it with intercepts. And by being able to do it with intercepts, it means that we can graph more than just y equals mx plus b. We can also graph equations like this. Okay, so that's all I wanted to show you with respect to intercepts. I want to pop over and look at something else in Desmos right now. So I want to talk about something called domain restrictions in Desmos. So one of the things that you're going to do today, and I'm going to put up an assignment on Google Classroom, is to create some Desmos art, right? And so you can create, Desmos art now that you have a better idea of how to make graphs. If I want a line that goes downhill, I would say I want y equals negative 2x, plus 7. And what I've got there is I've got, a line, but that line goes forever. I can zoom out, right? And that line just keeps on going. If I only want a segment of the line, which is what we're going to aim to do, our line segments cause us, if we only want a portion of it, we can implement these restrictions. Okay, so we can look at the restrictions. So say that I only wanted my line to go from the 3 over here to maybe the 6 on the x-axis. So I can use the curly parentheses, okay, so that guy, and I can say, oh, I want 3 to be on the low end, so 3 must be less than x, must be less than 6. And then I'm going to close that parenthesis. And what it does, if we actually look at the end point here, that is right at 3, and that is right at 6. So that's a domain restriction. And I can restrict it based off of the x values, or I could restrict it based off of the y values. So say that, you didn't care how far it went along the x-axis. But imagine that you didn't want any y values that were greater than 4. You wanted to stop that from happening. Well, same thing, curly parenthesis. And we're going to say, oh, I want my y value to be less than 4. And what it did then is it said, okay, you can do whatever you want as long as the y value doesn't get any higher than a y value of 4. Okay, so these are ways of doing restrictions. Now we could also do less than or equal to, and remember I just did that on my keyboard by pressing the equal sign and added that in, or you could pop this guy up and you could get the less than or equal to's or the greater than or equal to's out of there. So these things are called domain restrictions. So I've just shown you how to do a domain restriction. And what I'm going to have you do is I'm going to get you to check Google Classroom to see there's going to be a couple of assignments that I want you to do there. One of them is going to be a Desmos graphing assignment, okay? And the other thing that I want you to do is there's going to be more practice on finding intercepts. So there you go. Hopefully it's gone well today.